Welcome to the UGC EPG Pathshala lecture series in computer science. In this series of lectures, we have been looking at the subject software engineering. After having discussed more about the specification, design of the software development life cycle, we actually wanted to talk more about software testing. So this session talks more on the fundamentals of software testing. Some of the learning objectives for this session include the major intention of getting into testing. So if you look at testing, testing is just to execute a program. If it is a software, execute a code. So to execute a program with the intent of finding a error. So any error need to be found out as part of testing. To check if the system meets the requirements and be executed successfully with the intended environment. Initially we have specified or we have mentioned a list of requirements, and now as part of testing we are ensuring that all the requirements have been met, and to check if the system is fit for the purpose. So with what as a purpose we have started initially, we may have to match or fit to the actual purpose. And finally, we may have to check if the software does what it is expected to do. So anything that we wanted the system to do, we would have mentioned it as part of the requirement. So majorly to undergo the entire fitness of the specification that has been mentioned in the requirements phase, testing has been carried out. So error, majorly we call the computer errors as bugs. So we will try why this word of bug initially turned out with. So we have to define what is a computer bug. In 1947, Harvard University was operating on a room-sized computer, supercomputers, which was called Mark II, where mechanical relays, glowing vacuum tubes, technicians who programmed the computer by reconfiguring it, technicians also had to change the occasional vacuum tubes. So they were working on a room-sized computer, but a moth which flew into a computer and was zapped by the high voltage. So because of this high voltage, it landed on a relay and there was a bug which was identified. So this is one of the bug which initially started with when we were working with computers. So what are the other terms, related terms which we can project it for a bug? Bugs are also called as or also known as defect, fault, problem, error, incident, anomaly, variance, failure, inconsistency, product anomaly, product incidents, features. So these are some of the other synonyms of the word bug. So what do we mean by defective software? Are the softwares which are manufactured really being defective, or we call those as really defective softwares? So we try to develop programs that contain defects. After having mentioned the defects, we say how many defects involved or what kind of defects involved is the major challenge that we may have to find it out, or having assigned a person with the role of software test engineer or software tester, the responsibility of a software tester or a software test engineer is to identify how many bugs are really with the software, or how much defective is the software, or what kind of defects associated with the software. But it has really been hard to predict the future. By now you should have been aware of a word called Six Sigma, where we will try reducing the number of defects by where we wanted to assure the quality of the product. So we will come back to the Six Sigma. I just reminded of the word Six Sigma purely to reduce the number of defects, or making the software which is 99% defect free to 99.99% defect free. At no point in time we can say a product has 100% defect free. It will certainly have some bugs associated with it which can later be rectified, but then as a developer we can ensure to the stakeholders that this product is 99.99% defect free rather than saying 100% defect free. So predicting on these kind of defects, however, it is highly likely that the software which we develop in the future will not be significantly better. Some of the very common sources of problems which encounters or which comes across more defects in the software are: preliminarily, as a part of software development life cycle, we define requirements. So as part of requirements, there are plenty of possibility that we may not meet the requirements as specified by the user. So while testing, we may find these requirements as erroneous, incomplete and inconsistent. And it is not with the requirements phase alone, it can even be extended to the design also, where we find fundamental design flaws in the software. At the time of sketching or designing, we come across very fundamental issues with related to the software. We will discuss what these fundamental issues are. Even it could be carried till your implementation phase. Although it is sequential, an error that has happened either at requirements can be taken to implementation level, or an error which has happened fresh at the implementation level can also be a defective software. So mistakes in a chip fabrication, this is more common. Wiring, programming faults, malicious code, all these can happen as part of implementation level. And not only that, at the support system level, like poor programming languages, use of poor programming languages, people sometimes don't use optimized programming language also, which might also take us to a erroneous software. So faulty compiler and debugger, misleading development tools also might take us to a defective software level. Inadequate testing of software is the next criteria, where we have incomplete testing, we have poor verification, we find mistakes in debugging, and not only that, at the evolution or evolutionary phase, we have sloppy redevelopment or maintenance, introduction of new flaws in the attempt to fix old flaws. Any old flaws that we have come across with the intent of finding an error in the old flaw, we may come out with a new error also. So there can be incremental escalation to inordinate complexity. So those were some of the very common sources of problems which happen over different phases of the software development life cycle. But there can be adverse effects of these faulty softwares. Some of the adverse effects are in terms of communication. Say loss or corruption of communication media or non-delivery of data. If you typically look at space applications, because of these faulty softwares, there can be loss of life, there can be launch delays which can cost even more heavier. If you look at defense and warfare, it can misidentify a friend or a foe and it can lead to death. If you look at transportation, again we have deaths, delays, there can be sudden accelerations, inability to brake because of some faulty softwares. We will see some examples of these faulty softwares which has costed more. And safety critical applications like death, injuries are very common as part of faulty softwares. And with reference to electric power, again deaths, injuries, power outage, long-term health hazards like radiation might cause as part of faulty softwares. Money management is also been an adverse effect of faulty software, where we come across frauds, violation of privacy, shutdown of stock exchanges and banks, negative interest rates, and we have control of elections, control of jails, law enforcement. So everything is being remotely controlled by a software because of a faulty execution of a particular part of a code, need not be the entire software or a particular part of a code, this can produce adverse effects and can cost even the life. We will see a few examples which has actually happened as part of the implementation or this code. Say if you look at project Mercury's Fortran code, this had a faulty code mentioning a loop do I is equal to, it should have been 1 comma 10, instead of that the programmer has typed 1.10. So because of this fault, in an analysis of why the software did not seem to generate results, it was sufficiently accurate. So the erroneous 1.10 would cause the loop to be executed exactly once instead of 10 times to repeat. The software has executed this particular loop only once. For military aviation systems, with the faulty code, the problem still persisted. Supposing in the case of F-18 Aviation, where the plane got crashed because of a missing exception condition, if then without an else clause that was thought cannot be possibly arise. So this else clause is left with, and they did not think of a situation like that. Because of that, this F-18 airplane or military airplane has crashed. Simultaneously or similarly, in simulation, an F-16 program bug caused a virtual plane to flip over whenever it crossed the equator as a result of a missing minus sign to indicate south altitude. Even been experienced with ear ambiguities. You would have called, or you could recall, the problem of Y2K bugs. Here and again I have pointed out a fault similar to that. In 1992, Mary Bander received an invitation to attend a kindergarten in Winona, Minnesota, along with others who are born in 88. Mary was 104 years old at that particular point in time, and the other person who is an auto insurance rate tripled when he turned 101. So the computer program first driver over 100 and his age was interpreted as 1, because anything, the maximum age limit was said to be 100 and the computer has interpreted the age that has been mentioned as 101 as 1. So this was a blunder mistake that the computer has generated, which has landed in a faulty software. It did not stop with that, where it even extended to AT&T Bell Labs, where the bug on hello hello problem, where in mid December 1989 at the AT&T labs, where a new software is installed with 114 electronic switching systems. On 15th 1990, Jan 15th 1990, 5 million calls were blocked during a 9-hour period nationwide. So just look at the volume of number of calls which were blocked within a specific duration. For a duration of 9 hours, almost around 5 million calls were blocked, so the entire communication channel was cut. So this is primarily because of switch statement break, which did not run as part of the C program. And there is another problem which happened at the bank level also. A Norwegian bank ATM consistently dispersed 10 times the amount required. So every time when we insert the ATM card and if we ping in an amount, it dispersed 10 times the amount that we have seeked in for. So many people jealously joined the queues as the news widespread. A software flaw caused UK bank to duplicate every transfer payment request for half an hour. So the bank lost almost around 2 billion British pounds. So the bank eventually recovered the funds but lost £500,000 in potential interest. So that is the problem with the bank even. So those were run. And very interestingly, in terms of making a rupee, an Australian man purchased worth of Sri Lankan rupees. The next day he sold the rupees to the bank, to another bank, for 4 times that of the actual price with which he has got with. So the first bank software had displayed a bogus exchange rate in a rupee position. So it was not the fault of the person. Instead, it was the fault of software which got executed, it has shown the exchange rate more than what it is in the actual market value. So there happened to be a court case and the judge ruled that the man had acted without intended fraud and could keep the extra amount with himself. And there is another bank related bug which got displayed in a bank of New York, which actually had a 32 billion overdraft as a result of 16-bit integer counter that went unchecked. So the same Bank of New York was unable to process the incoming credits from security transfers, while New York Federal Reserve automatically debited New York cash account. So all these are said to have produced adverse effect purely because of the faulty executions of software. So you can simply think, if it happened to have existed only during the implementation phase, or it should have happened from the beginning or from the specification point of view. So as part of specification we have read, or we have rather experienced, if you can't say it, you can't do it. You have to know what your product is before you can say if it has a bug. That means a specification defines the product being created and includes two different terms. One is a fundamental requirement, the other one as functional requirement and non-functional requirements. So as part of functional requirements, we tend to describe the features the product will support. That is a word processor which has a save, print, check spelling, check font, wherein we can make alternate changes to, if in case of faulty execution. And in case of non-functional requirements, there are constraints on the software or the products. For example, we may have to actually rely on the security, reliability, user friendliness and the platform with which we are to develop the work. Now we will try understanding certain rules which the software bug has to come across. So a software bug occurs when at least one of these rules is true. So it is certainly dependent on all these 5 software terms. So software does not do something that the specification says it should do. So it does not do anything more on top of what the specification has actually mentioned. That is what we are tending to say here. The software does something that the specification says it should not do. So a software behaves unnaturally or rides on top of the specifications that this has to do something more than what the specification has mentioned. The third is the software does something that the specification does not mention, which is in similar case with the previous one. The software does not do something that the product specification does not mention, but it should have mentioned. So as a part of product specification, we should have mentioned some point, but then we are trying to adopt it with the software. Now as a developer, I will try mapping with the specification, and it was found to be an error by a third party or a person who has been assigned a role called testing engineer. So a testing engineer sees the specification and matches with the product that has been developed and sees there is no connection between what has been developed and what has been specified, so it has been pointed out as a error. And finally, the software is difficult to understand, hard to use, and it's been slow. So because of all these 5 reasons, there can be software bugs that can happen during the development. So what would be the impact of these bugs during the entire phase of software development life cycle? So most bugs are not because of mistakes in the code. So not only in the code, as I have already pointed out, it can be at any point that we have done it in the previous case. Say as part of software development life cycle, it can start from the beginning, that is at the requirements analysis and specification level. So 55% of the bugs turn out at the requirements analysis and specification level. Approximately 25% of the software bugs turns from the design level. Only 15% happens to be at the implementation or code level, and the rest of the things, risk management, other stuffs, happens at only with 5%. After having done the fault in the software. Now mapping it with the code, how much would it cost when we try to execute the faulty software. So relative cost of bugs found later cost more to fix. So cost to fix a bug increases exponentially in the power of 10 to the power of x. That is, it is tenfold as time increases. Supposingly, a bug found during specification costs $1 to fix. So at the time of specification, if I find $1 is the actual amount to fix this bug, if found in the design, it would be $10. And if the same thing is found as the code level, it would take $100. And the same if found during the released software, it would cost $1,000. So it is a tenfold increase that we could see it when it goes to the next level, subsequent levels. Is it really been possible to develop a bug-free software? As I have already mentioned, Six Sigma is one of the terms wherein we ensure that we bring the software or we bring any product which is 99.99% defect free rather than saying 100%. So it is pretty much possible, but then we may have to take appropriate measures wherein we ensure that the bugs are not associated. So software is in the news for the wrong reason, in terms of security breach, in terms of mass land cost, hackers getting credit card information and etc. So why can't software engineers develop software that just works? So as software gets more features and support more platforms, it becomes increasingly difficult. So this is quite natural. So as you increase with the number of features that the software has to support with, or if you wanted the software to execute in over different platforms, then obviously it is very difficult for us to execute the complete of the software without any bug. So specify or limit yourself with the number of features, rely on only one platform, one or two platforms, then we can create a bug-free software. This is a very simplistic solution that we can provide. And do you think bug-free software is unattainable? As I have already pointed out, it is pretty much possible, but then we may have to take appropriate measures accordingly. So are there technical barriers that make this impossible? Certainly not. Is it just a question of time before we can do this? Are we missing technology or process? Not really. So what are the goals of a software tester as part of testing? So the goal of a software tester is to initially find bugs and to point out all the bugs as early in the software development process as possible. So it is not just to find error, but then we may have to find the error as early as possible, so that if it is mentioned at the specification level, map it with the cost. If it is mentioned at the design level, map it with the cost. So we may have to reduce the cost of the faulty software and make sure that they get fixed very early. One of the pure advices that we can make it out as part of software test is be careful not to get caught in the dangerous spiral of unattainable perfection. So what are the basic expectations on a software engineer? You can ask whether the software engineer or software tester as an explorer or a troubleshooter, or are they relentless, are they creative, are they perfectionist, do they exercise good judgment, are they tactful and diplomatic, are they persuasive? So they have to be all in one. After having looked at various examples of testing or a faulty software, and what do we need to do in order to find out software bug? Now that it is time for us to understand what is testing. So in this particular context need not be a software, but then it is for almost all the products that we are trying to develop. But here I am making it very clear to define the testing in terms of software. Anything which confirms change of behavior, or change of behavior is supposed to be an error. So in this context we are confirming that a correct behavior of a piece of software need to be ensured so that It is the actual role of a tester. So we may have to ensure that the intended behavior of a software need to be achieved. So why should we test? We know that we intended the code to do this task. So after having defined a list of characteristics, properties and things like that, we were intending the software to perform a certain task, and we need to confirm that it does what it is supposed to be intended with. So we wanted, or we have specified rather, a software to do a specific task, and the role of software tester is to ensure that it is done in the mentioned way. So how to test our tests? In other words, how can we be sure our tests are testing the right stuff, testing most of the code and not just repeatedly testing the same code. So we may not have to test the same code again and again, rather we may have to ensure that most of the code is getting tested rather than one part of the code. Looking at very common testing principles, so to attain a very good testing, some of the practices need to have mentioned. So some good testing practices include, a good test case is one that has a high probability of detecting an undiscovered defect, not one that shows that the program works correctly. So this should not have been discovered, not that all these lines of code or the program or a module which has been executed correctly. It is not the intention with which we find the parts of the code which are executing correctly, rather it is the intention of identifying the undiscovered defects. It is impossible to test your own program, so it has been given to a third party or a tester who tests what it is intended to do. A necessary part of every test case is a description of the expected result. So we may have to avoid non-reproducible or on-the-fly testing. So we should not try doing on-the-fly mode of testing any softwares, and we may have to write test cases for valid as well as invalid input conditions. Thoroughly inspect the result of each test. So every time when we inspect on the software, we may have to thoroughly inspect on all the results of each of the test cases that we have undergone with. In short, as a summary of this particular session, we have started with the fundamentals of software testing, where what the program is intended to do with right at the specification, it has to meet till the last phase of the software development life cycle. So we have started defining on what the software testing is, where it is to execute a program with the intent of finding an error. Further, I have described few examples, or I gave few examples wherein the faulty software costed us much, either in terms of lives or in terms of the cost associated with it. And it is more likely to see more on the different types of testing, which are like unit testing, integration testing, system testing and acceptance testing. Thank you.